let's think about polymers. Big problem with polymers is they're soft and floppy. They're not very strong. But we can have a look at it in two ways. It's the old, is the glass half full or half empty? Here it's half full because we're using the elastomeric properties of the polymer to do something useful. There's the half empty case where it's not performing the function that we need. So you've got to be very careful when we talk about properties. Each material has a range of properties. Some make it not that useful for us, others do. So, as I said, the polymers, the things we like, they're flexible, they're good insulators, but they have these problems. So how might we go from there and include some of this in there? And that's where we can come into nanomaterials. Size matters when it comes to nanomaterials because things behave quite differently. So what happens when we go from macro to nano? What properties change? How do they change and why? Think about one copper atom. One copper atom will not have any stiffness. Stiffness. It won't have any stiffness. And it won't conduct electricity because it's got nowhere to send its valence electrons. A lump of copper has stiffness and does conduct electricity. What about 1,000 atoms? That's about a 3 nanometer length nanoparticle. How will that behave? Will it behave more like that or more like that? I don't know. But that's what makes it a little bit interesting. We have to think, what's going on here? Where does this fit into this screen? And how small do we have to go to make it start to behave like that? Another couple of examples. If I take copper, it has a stiffness of 100 gigapascal and a hardness of 150. If I make the grains nano size, the stiffness is 300 gigapascal and the hardness 300. If I take a ceramic, these are the values here. Again, you can see I've increased strength and hardness by making nanostructured material. So that's all very good. Other things. If we take gold, melts at 1064 degrees. I have a lump of gold. If I make the particle size about 1.5 nanometers, it melts at 500. At UTS, some colleagues have got it to melt down around here. They've made about 1 nanometer particles. And the end result is they coated a plastic car because it wasn't going to melt the plastic. So we get this change in melting point. I already mentioned changes in colour. So by controlling the nanoscale, we can control these sorts of properties. We can get fluorescence of semiconducting nanocrystals as well, down at the nanoscale. The first nanotechnologist, we might argue, is stained glass. Stained glass, they use gold nanoparticles. And if they have this around 25 nanometers, it's red. So this is a gold colloidal suspension. Gold nanoparticles, red. They're around that size. I think they're about 30 nanometers. Okay. So we've gone from gold to that, or just changing the size. And if we have different nanometer sizes, we can have different colours. And that's what that says the first nanotechnologists used to stain the glass. These nanoparticles. This is a stable suspension. That's been like that for about 3 years now. Rutherford did the same thing 150 years ago, and it's still stable. But it tends to crash out. If I poured some into a dirty beaker or stuck my finger in there, the water suspension would just collapse. So So we get those sorts of things from there. It's a plasmonic response. So we have all these things changing. If we have magnetic properties, I've got some, I meant to get a screw and put on the thing and show you, but this is a ferrofluid. So it's got iron nanoparticles in there, and I don't know if you can see it. The stains, it's hard to see. But they're iron nanoparticles that become super paramagnetic simply because of their size. The grains, the actual size of the particle is less than the domain size. So why do we see these things? For example, what about melting point? Why, as I go smaller and smaller, does the melting point change so dramatically? Well, another example here, 3 nanometer cadmium selenium nanocrystal melts at 427 compared to 1400 degrees for bulk material. Well, it comes down to this. This is a scale of size of things. And if we look at here, the electron wavelength, it's around there. Up here, we can treat the electrons as hard spheres. Down there, we have to treat electrons as mushy clouds. It's the only way we can describe what's going on. And we find that above that line, it's still the sensible world of Sir Isaac Newton and his physical laws. So I walk across this room here, I'm relying on Isaac Newton's laws. That's how I can walk across there. It's the world we commonly experience. We know, we feel, we have an intuition of what's going to happen. When we get down here, it's quantum mechanics. And I know about this much about quantum mechanics. But mushy electron waves take over, and generally our Newtonian instincts and assumptions are wrong. It becomes very difficult for anyone who's not into quantum mechanics to understand what's going on. And here's a couple of examples of what can go wrong. This is for a DLP projection screen. What they have is these little cantilevers that bend up and down depending on the voltage applied here. It reflects the light at different angles. It gives us our television screen. This is what happened. These longer ones just came down and stuck. They welded themselves to the substrate simply because of moisture. Now, if I had a cantilever that been this way, there's no way it would stick to the other surface just due to moisture. Come back to why in a second. Here's another example. This is not nanoscale, but it's small, 30 micron, speeds at 300,000 RPM. It seized after 477,000 rotations. It's 95 seconds. The reason, Van der Waals bonding. Now, at my scale, I don't have to worry about Van der Waals forces. It's not a problem. And at that scale, it becomes very important. Why? Well, at my scale, I'm very concerned about momentum. That's what I'm concerned about. And I'm a little bit bothered with friction. And I can ignore surface tension, charging, Van der Waals forces. In my everyday life, I don't have to worry about that. The balance of forces changes as things get smaller. Momentum is proportional to mass, which is proportional to volume, which is L cubed. Okay, L's my length. But all of the other ones, these things here, depend on contact area, L squared. So, if I do the maths here, if I go from, say, 1 metre to 1 micron, my mass and momentum is 10 to the 18 times smaller, and my surface-dependent things are 10 to the 12 times smaller. That means that friction, surface tension, van der Waals forces are 1,000,000 times more important than microscale. And it means it's 1,000,000,000 times more important than nanoscale. So that's the first thing we have to come to grips with in nanotechnology. These sorts of things become much more important down at that level. The other thing is, let's go here, is that if I have one atom here and all these atoms there, then if I have these as the surface atoms, we compare the ratio of surface atoms to the atoms in the volume, it gets very small, or it gets very large. So that at about 1 nanometer, 50% of the atoms are on the surface. And we know that surface atoms have much different energy levels to atoms in the center. That's why that's why I form these little beads here, because the surface atoms have this surface energy level with everything in place. So my surface atoms behave quite differently to the atoms in the centre. And at the nanoscale, I have just as many surface atoms as I have bulk atoms. So we might expect the nanomaterials to behave a little bit differently. So let's have a look at some examples and try and see where all this fits in. If I want to make nanomaterials, I've got two choices. One is a top-down approach. So we start off with this, and we go to that. So I take my material and I make it smaller somehow. I grind it, cut it up, chop it up, laser ablate it. A whole range of ways to make small nanoparticles. That's one way to do it. The other way is from the bottom-up approach, where I take individual pieces of material and build some sort of structure. We're going to talk pretty much about this. So how can we do that? We can do some clever chemistry. As I said, I'm not going to give a lot of detail here. But we can make these micelles where this end is, say, water-loving and this end is hydrophobic, and we put it in some sort of hydrocarbon solvent. And this here, this micelle, acts as a little nanoreactor. So the example here is cadmium sulfide. I mix this thing here, I'm not even going to try and say it, with similar micelles as sodium sulfide. They mix together and the reaction can only take place within that micelle. So if I control the size of that micelle, I control the size of my nanoparticle. So back at UTS, I run a subject nanomaterials. We make zinc sulfide particles. And we change the size of that micelle to give us different size zinc sulfide particles. So we call it a nanoreactor. Or I call it a nanoreactor anyway. So we can control that simply by controlling what surfactant I use here. I can use any of the deposition techniques such as chemical vapor deposition or physical vapor deposition. And if I'm clever, I can change things so I can deposit different materials at different times in different places. So I can have a layer mode, an island mode, a mixed mode, and that will depend on my operating conditions. So I can make pillars, I can make films, I can make all sorts of things there. The other one is self-assembly. The reason is that it's very difficult for us to, I can make particles, but what I'd like to do is make some sort of structure. So I want to assemble those particles into some sort of thing to do something. So we can